Listening practice, a detailed expansion of Chapter 1, Introduction to Structural Design, focusing on foundational concepts for engineers, architects, and students. Chapter 1, Introduction to Structural Design 1.1 Principles of Structural Engineering, Core Objectives, Safety, Functionality, Economy, and Aesthetics. Historical context, evolution from ancient masonry to modern skyscrapers. Fundamental concepts, equilibrium, balancing forces and moments, sigma F equals 0, sigma M equals 0. Compatibility, ensuring deformations align with material behavior. Material behavior, elasticity, plasticity, and ductility. Role of sustainability, minimizing environmental impact through efficient design, e.g., lightweight structures, recycled materials. Ethics in design, prioritizing public safety over cost cutting. 1.2 Loads and forces in structures, types of loads, dead loads, permanent weights, e.g., self-weight, fixtures. Live loads, variable forces, e.g., occupants, furniture. Environmental loads, wind, seismic, snow, and thermal effects. Load combinations, code-based approaches, e.g., ASCE 7-22, Eurocode and 1990. Extreme event considerations, e.g., 100-year storms, earthquakes. Load paths, transfer mechanisms, e.g., beams, columns, foundations. Importance of redundancy and load redistribution, e.g., trusses versus moment frames. Case study, wind load analysis in the Burj Khalifa, buttressed core system. 1.3 Safety, stability, and serviceability, ultimate limit states, ULS, strength failure, e.g., buckling, shear, bending, collapse prevention, e.g., ductile versus brittle failure modes, serviceability limit states, SLS, deflection limits, e.g., L/360 for floor beams, vibration control, e.g., footbridges, tall buildings, crack width limits in concrete. Design philosophies, allowable stress design, ASD conservative safety margins. Load and resistance factor design, LRFD probabilistic reliability. Stability consideration, overturning resistance, e.g., retaining walls. Lateral stability systems, e.g., shear walls, braced frames. Case study, the Hyatt Regency Walkway Collapse, 1981, Lessons in Connection Design and Load Path Integrity. Key takeaways, structural design balances physics, materials science, and human needs. Codes, e.g., IBC, Eurocodes, standardize safety but require engineering judgment. Modern tools, FIA, BIM, enhance precision but do not replace foundational principles. Discussion questions, 1. How do material choices influence load-bearing capacity and failure modes? 2. Why might a structure meet strength requirements but fail serviceability criteria? 3. What ethical dilemmas arise when optimizing cost versus safety? This chapter sets the stage for deeper exploration of materials, Part 2, and project execution, Part 3, emphasizing the interdependence of theory, analysis, and real-world constraints. Here's a detailed expansion of Chapter 2, Materials in Structural Design, focusing on material properties, modern innovations, and decision-making frameworks for engineers and designers. Chapter 2, Materials in Structural Design 2.1 Steel, Concrete, and Timber, Properties and Applications. Steel, Properties, High Tensile/Compressive Strength, Ductility, Weldability, Recyclability. Applications, Skyscrapers, Bridges, Industrial Frames. Types *, Carbon steel, Stainless steel, Weathering steel. Limitations, Susceptibility to corrosion, Fireproofing requirements. Case study, the Eiffel Tower, wrought iron to modern steel retrofitting. Concrete, properties, high compressive strength, low tensile strength, improved with rebar. Types, normal strength, high performance, self-compacting, fiber reinforced. Applications, dams, foundations, pavements, precast elements. Innovations, ultra-high performance concrete, UHPC, 3D printed concrete. Case study, Hoover Dam, mass concrete placement challenges. Timber, properties, lightweight, renewable, carbon sequestering. Engineered wood, Glilam, cross-laminated timber, CLT, LVL. Applications, residential buildings, low-rise commercial structures, bridges. Challenges, moisture sensitivity, fire resistance, termite protection. Sustainability spotlight, the Mjøstrene Tower, 18-story timber high-rise in Norway. Comparison table, material compressive strength tensile strength sustainability cost, relative, steel high very high concrete very high low moderate timber moderate high moderate 2.2 advanced materials, composites, polymers, smart materials, fiber reinforced polymers, FRP, carbon fiber, CFRP high strength to weight ratio, aerospace, retrofitting bridges. Glass fiber, GFRP corrosion resistant, marine structures. Applications, strengthening concrete beams, lightweight trusses. Polymers, thermoplastics, PVC pipes, geomembranes. Thermosets, epoxy resins for adhesives, coatings. Smart materials, shape memory alloys, self-repairing structures, e.g., seismic dampers. Self-healing concrete, microcapsules or bacteria, e.g., Bacillus subtilis, to seal cracks. Piezoelectric materials, energy harvesting from vibrations, e.g., pavements. Case studies, Boeing 787 Dreamliner, composite fuselage for weight reduction. Solar Impulse 2, polymer-based solar aircraft. 2.3 Material selection criteria, key factors, 1 Mechanical properties, strength, stiffness, ductility, fatigue resistance. 2 Environmental resistance, corrosion, UV degradation, fire rating. 3 Cost, initial versus life cycle costs, maintenance, durability. 4 Sustainability, embodied carbon, recyclability, LEED/BREEAM compliance. 5 Fabrication, ease of manufacturing, tolerances, lead times. 6 Aesthetics, surface finish, color, texture. Decision frameworks, Ashby charts, plotting material properties, e.g., strength versus density. Multi-criteria decision analysis, MCDA, *, weighted scoring for trade-offs. Digital tools, Granta EDU Pack, CES Selector. Case study, Sydney Opera House, transition from concrete shells to precast segments for cost and time efficiency. Key takeaways, traditional materials dominate due to proven reliability, but advanced materials enable groundbreaking designs. Sustainability is reshaping material choices, e.g., timber's resurgence, low-carbon concrete. Selection requires balancing technical, economic, and environmental priorities. Discussion questions, 1. When would you choose engineered timber over steel for a mid-rise building? 2. How might self-healing materials reduce life cycle costs in infrastructure? 3. Debate, should governments mandate low-carbon materials in public projects? This chapter bridges the gap between material science and practical design, preparing readers to evaluate material trade-offs in real-world projects. Part 2, Materials Analysis, will delve deeper into testing and failure modes, while Part 3, Project Management, addresses cost and scheduling challenges tied to material choices. Chapter 3, Structural Systems and Configurations 3.1 Framed, Shell, and Truss Structures, Framed Structures, Definition, composed of linear elements, beams, columns, connected to form a rigid skeleton. Applications, commercial buildings, residential complexes, industrial facilities. Advantages: flexibility in layout, ease of construction, adaptability to various cladding materials. Limitations: requires robust foundations, lateral stability challenges in tall structures. Examples: steel-framed skyscrapers, reinforced concrete parking garages. Innovations: hybrid systems, e.g., framed structures with composite materials. Shell structures, definition, curved surfaces, domes, vaults, that distribute loads through membrane stresses. Applications: stadium roofs, aircraft hangars, water tanks. Advantages: high strength-to-weight ratio, aesthetic versatility. Limitations: complex formwork, sensitivity to localized loads. Case study: the Sydney Opera House, precast concrete shell segments. Truss structures, definition, triangular units forming rigid frameworks to span long distances. Applications: bridges, transmission towers, roof supports. Advantages: efficient load distribution, lightweight, cost-effective for large spans. Limitations: susceptibility to buckling in compression members. Example: the Eiffel Tower, iron truss system. Comparison table: system load distribution, material efficiency, span capability framed linear moderate short mid shell surface high large truss triangulated high very large 3.2 high-rise buildings and bridges, high-rise buildings, design challenges, wind sway, seismic resilience, vertical transportation. Lateral systems, core and outrigger, central concrete core with outrigger beams, e.g., Burj Khalifa. Shear walls, reinforced concrete walls resisting lateral forces. Diagram rids, exterior diagonal frameworks, e.g., the Shard, London. Innovations, tuned mass dampers, modular construction. Case study: Taipei 101, 660-ton tuned mass damper for typhoon resistance. Bridges, types, beam bridges, simple spans, e.g., highway overpasses. Arch bridges, compression-based, e.g., Sydney Harbour Bridge. Suspension/cable stayed, long span solutions, e.g., Golden Gate Bridge. Load considerations, dead loads, traffic dynamics, environmental forces. Sustainability, use of weathering steel, recycled materials. Case study: Millau Viaduct, record-breaking cable-stayed bridge in France. 3.3 Retrofitting and rehabilitation of existing structures, reasons for retrofitting, aging infrastructure, seismic code updates, increased load demands. Sustainability goals, reusing structures versus demolition. Techniques, strengthening, carbon fiber reinforced polymer, CFRP, wraps, for concrete columns. Steel bracing, adding lateral support to framed buildings. Damping systems, base isolators, viscous dampers. Material upgrades, replacing corroded rebar, epoxy injections for cracks. Challenges, balancing historical preservation with modern safety standards. Minimizing disruption during construction, e.g., hospitals, bridges. Case studies: San Francisco City Hall, seismic retrofit using base isolation. Brooklyn Bridge, rehabilitation of corroded steel cables. Tools, non-destructive testing, ultrasonic, ground-penetrating radar. Key takeaways: structural systems dictate a project's form, function, and feasibility. Retrofitting merges engineering ingenuity with sustainability, extending structural lifespans. Innovations like modular construction and smart materials are redefining traditional systems. Discussion questions: 1. Why might a shell structure be unsuitable for a high-rise building in a seismic zone? 2. How does the choice of a bridge type impact environmental and community considerations? 3. Should retrofitting prioritize historical authenticity or modern safety standards? This chapter equips readers to evaluate structural systems holistically, balancing technical, aesthetic, and sustainability factors. It sets the stage for advanced materials analysis, Part 2, and underscores project management challenges, Part 3, such as coordinating multidisciplinary teams in retrofitting projects. Chapter 4, Analytical Methods in Structural Design 4.1 Stress-Strain Analysis Fundamental Concepts, Stress, Force per Unit Area, Sigma equals F/A. Types, Tensile, Stretching, Compressive, Squeezing, Shear, Sliding. Strain, Deformation per original length, Epsilon equals delta L/L. Types, Normal, Axial deformation, Shear, Angular distortion. Stress-strain curve, Elastic region, Hooke's law, Sigma equals E epsilon, where E equals modulus of elasticity. Yield point, Onset of plastic deformation. Ultimate strength and fracture. Applications, Material selection, e.g., steel's ductility versus concrete's brittleness. Safety checks, ensuring stresses remain below yield strength. Case study, Tacoma Narrows Bridge Collapse, 1940, resonance-induced shear stress failure. 4.2 Finite Element Analysis, FEA, Process and Principles, 1 Discretization, Mesh Generation, Elements, Beams, Shells, Solids. 2 Boundary Conditions, Constraints, Fixed, Pinned, and Loads, Static, Dynamic. 3 Solving, Matrix Equations, Ku equals F, where K equals stiffness matrix. 4 Post-processing, visualizing stress contours, deformations. Advantages, handles complex geometries and material nonlinearity. Predicts hotspots, e.g., stress concentrations at notches. Limitations, computational cost for large models. Accuracy depends on mesh quality and assumptions. Software, ANSI, Abacus, COMSOL. Case study, aircraft wing analysis optimizing weight and strength using FEA. 4.3 Dynamic and seismic analysis. Dynamic analysis, natural frequency, F equals 1/2 pi, m/k, where m equals mass, k equals stiffness. Resonance, avoiding frequency matching, e.g., footbridge vibrations. Damping, energy dissipation, e.g., viscous dampers. Seismic analysis, response spectrum, plot of max acceleration versus structure's natural period. Design approaches, equivalent lateral force, ASCE7 simplified method. Time history analysis, ground motion simulations. Innovations, base isolation, e.g., rubber bearings in San Francisco City Hall. Energy dissipation devices, e.g., tuned mass dampers in Taipei 101. Case study, 2011 Tohoku earthquake performance of base isolated buildings. Key takeaways, stress-strain analysis underpins material behavior understanding. FEA bridges theory and reality, enabling virtual prototyping. Dynamic/seismic analysis ensures resilience against unpredictable forces. Discussion questions, 1. How might residual stresses from manufacturing affect FEA results? 2. Why is resonance a critical consideration in both dynamic and seismic analysis? 3. Debate, should all new buildings in seismic zones require base isolation? Equations to highlight, Hooke's law, sigma equals E epsilon, natural frequency, F equals 1/2 pi, K/m, stiffness matrix, Ku equals F. Visual aid suggestions, stress-strain curves for steel versus concrete. FEA mesh of a cantilever beam under load. Response spectrum comparison for different soil types. This chapter integrates mathematical rigor with practical applications, preparing readers to tackle real-world structural challenges through advanced analytical techniques. Chapter 5, Codes, Standards, and Compliance. 5.1 International Building Codes, IBC, Eurocodes, Purpose, ensure safety, accessibility, and resilience in structural design. IBC, International Building Code, scope, widely adopted in the U.S., addresses fire safety, structural integrity, and occupancy. Key sections, load requirements, ASCE 7, material standards, ACI, AISC, seismic design, Chapter 16. Updates, cyclical revisions, e.g., 2024 IBC emphasizes climate resilience. Eurocodes, scope, Pan-European standards, N 1990 to 1999, harmonized across EU member states. Key features, modular structure, N 1990, basis of design, N 1992, concrete. Geographic flexibility, nationally determined parameters, NDPS, for regional adaptation. Comparison, aspect IBC Eurocodes region U.S centric Europe approach prescriptive performance-based materials emphasizes steel/concrete broader material inclusivity, case study, One World Trade Center compliance with NYC building codes and IBC post 9/11 security updates. 5.2 Sustainability certifications, LEED, BREEAM, LEED, Leadership in Energy and Environmental Design, criteria, energy efficiency, water conservation, material reuse, e.g., recycled steel, levels, certified, silver, gold, platinum. Impact on design, integrated solar panels, green roofs, low-carbon concrete. BREEAM, Building Research Establishment Environmental Assessment Method, criteria, life cycle assessment, pollution reduction, ecological site selection. Scoring, pass, good, very good, excellent, outstanding. Regional focus, strong adoption in Europe and the Middle East. Comparison, aspect lead BREEAM region global, US dominance, Europe/UK focus energy/water efficiency holistic life cycle impact innovation awards innovation credits less flexible criteria, case study, The Edge, Amsterdam BREEAM outstanding certification via smart lighting and energy neutral design. Emerging trends, net zero carbon frameworks, circular economy principles. 5.3 Ethical and legal responsibilities, ethical obligations, public safety, prioritize safety over cost or aesthetics, e.g., avoiding flammable cladding. Transparency, disclose conflicts of interest, e.g., material supplier partnerships. Sustainability, advocate for low-carbon materials even if not legally required. Legal frameworks, liability, professional negligence, e.g., design flaws causing collapse. Contracts, adherence to project specifications and timelines. Consequences, fines, license revocation, or criminal charges for code violations. Case studies, Grenfell Tower Fire, 2017 ethical failure in cladding choice leading to 72 deaths. Hyatt Regency Walkway collapse, 1981 legal liability for unapproved design changes. Global challenges, balancing local codes with international projects, e.g., Dubai's Burj Khalifa meeting both UAE and Eurocode standards. Key takeaways, codes, IBC, Eurocodes, set baseline safety, certifications, LEED, BREEAM, drive sustainability. Ethical practice bridges legal compliance and moral duty to society and the environment. Globalization demands fluency in multiple standards for cross-border projects. Discussion questions, 1. How might a conflict arise between client budget constraints and LEED/BREEAM goals? 2. Should engineers be legally liable for decades-old designs if new codes deem them unsafe? 3. Can sustainability certifications ever replace building codes? Why or why not? Visual aids, flowchart, steps to achieve LEED certification in a high-rise project. Map, global adoption of IBC versus Eurocodes. Timeline, key legal cases shaping structural engineering ethics. This chapter underscores the symbiotic relationship between regulatory frameworks, voluntary sustainability goals, and ethical imperatives, equipping professionals to navigate complex compliance landscapes. Chapter 6, Innovations in Structural Design 6.1 Computer-Aided Design, CAD, and Building Information Modeling, BIM, Evolution of CAD, Transition from 2D Drafting, e.g., AutoCAD, to 3D modeling, enabling precise visualization and iterative design. BIM Revolution, Collaboration, Centralized Platform for Architects, Engineers, and Contractors, e.g., Autodesk Revit. Clash Detection, Identifying conflicts between systems, e.g., HVAC versus structural beams, pre-construction. Life Cycle Management, Integrating data for maintenance, energy analysis, and renovations. Software tools, AutoCAD, Traditional CAD, Revit, BIM, Navisworks, Coordination. Emerging Trends, Generative Design Algorithms Optimizing Material Use. Case example, Shanghai Tower BIM streamlined its twisted, energy-efficient design, reducing rework by 30%. 6.2 3D Printing and Modular Construction, 3D Printing, process, layer-by-layer extrusion of materials, concrete, polymers, to create walls, bridges, or entire homes. Benefits, custom geometries, e.g., organic shapes, reduced waste, rapid prototyping. Challenges, limited material codes, scalability for large projects. Pioneers, Icon, affordable housing, COBOD, multi-story structures. Modular construction, off-site fabrication, factory-built modules, e.g., bathrooms, hotel rooms, assembled on-site. Advantages, faster timelines, consistent quality, reduced site disruption. Sustainability, lower carbon footprint through efficient material use. Synergy, 3D printed modules, e.g., mighty buildings prefab homes, combine customization with speed. Case examples, B2 Tower, Brooklyn, world's tallest modular residential building. Dubai's 3D printed office, completed in 17 days with 50% cost savings. 6.3 Case Study, the Burj Khalifa, Structural Innovations, Buttressed Core, Y-shaped reinforced concrete core for lateral stability, inspired by Islamic architecture. High-strength concrete, up to 80 MPa compressive strength, with ice-cooled mixes to combat Dubai's heat. Wind engineering, tapered silhouette and helical design reduced wind loads by 30%. Construction techniques, climbing formwork, automated systems enabled vertical progression at one floor/week. Material logistics, over 330,000 cubic meters of concrete delivered via a pipeline system. Technology integration, CAD/BIM, 3D models, coordinated MEP systems and spire alignment. Wind tunnel testing, validated aerodynamic performance, preventing vortex shedding. Legacy, set benchmarks for super tall skyscrapers, influencing designs like Jeddah Tower. Key takeaways, BIM transforms collaboration and life cycle management, while 3D printing and modular methods redefine construction speed and sustainability. Burj Khalifa exemplifies how innovation in materials, design, and technology overcomes extreme engineering challenges. Future trends, AI-driven design, bioconcrete, and space-efficient modular cities. Discussion questions. 1. How might generative design in BIM address urban housing shortages? 2. Can 3D printing replace traditional construction in disaster relief scenarios? 3. What ethical considerations arise when pushing structural limits in skyscrapers? Visual aids, BIM workflow diagram versus traditional CAD. Timeline of 3D printing milestones in construction. Cross-sectional infographic of Burj Khalifa's buttressed core. This chapter illustrates how cutting-edge tools and methods are reshaping structural design, balancing ambition with practicality, and sustainability with ingenuity. Chapter 7, Fundamentals of Materials Science 7.1 Atomic Structure and Material Behavior, Atomic Bonding, Metallic Bonds, Delocalized electrons enable conductivity, e.g., copper, aluminum. Covalent bonds, shared electrons create rigidity, e.g., diamond, quartz. Ionic bonds, electron transfer leads to brittleness, e.g., NaCl, ceramics. Crystal structures, BCC, body-centered cubic iron at room temperature. FCC, face-centered cubic aluminum, copper. HCP, hexagonal close-packed titanium, magnesium. Defects and their impact, point defects, vacancies, interstitials, affect diffusion and conductivity. Dislocations, govern plasticity and ductility. Grain boundaries, influence strength and corrosion resistance. Case study, graphene is single-layer carbon lattice with exceptional strength and conductivity. Comparison table, atomic structures and properties material class bonding type example key property metals metallic iron, Fe, high ductility ceramics ionic / covalent alumina, allo, high hardness polymers covalent / van der Waals polyethylene low density 7.2 mechanical, thermal, and chemical properties, stress strain curve, elastic region, Hooke's law, sigma equals E epsilon, yield point, plastic deformation. Hardness, resistance to indentation, e.g., Vickers test for steel. Toughness, energy absorbed before fracture, e.g., rubber versus glass. Thermal properties, conductivity, metals, high, e.g., silver, versus polymers, low, e.g., PVC. Expansion, coefficient of thermal expansion, CTE, impacts joint design, e.g., bridges. Phase changes, melting points, tungsten's high MP versus solder's low MP. Chemical properties, corrosion, oxidation in iron, rust, versus passivation in stainless steel. Reactivity, alkali metals, e.g., sodium, versus noble metals, e.g., gold. Environmental degradation, UV breakdown of polymers. Case studies, 1 stainless steel, chromium oxide layer prevents corrosion in harsh environments. 2 silicon in semiconductors, covalent bonding enables precise electron control. Key takeaways, atomic bonding and crystal structure dictate material behavior. Mechanical properties, e.g., strength, ductility, are rooted in defects and bonding. Thermal / chemical stability determines applications, e.g., jet engines, marine structures. Discussion questions, 1. How does the FCC structure of aluminum contribute to its formability? 2. Why might a material with high thermal conductivity be unsuitable for insulation? 3. How do grain boundaries in metals influence both strength and corrosion? Visual aid concepts, diagram, stress strain curves for brittle versus ductile materials. Crystal structure models, BCC, FCC, HCP. Corrosion mechanisms, e.g., galvanic series. This chapter bridges atomic scale principles to real-world material performance, setting the stage for advanced testing, Chapter 8, and failure analysis, Chapter 9. Chapter 8, Testing and Characterization 8.1 Destructive versus non-destructive testing, NDT, destructive testing, DT, methods, tensile testing, impact testing, Charpy/IZAD, hardness testing, Rockwell, Brunel, applications, determining ultimate strength, ductility, and failure modes. Advantages, provides precise mechanical property data. Limitations, renders the sample unusable, not ideal for in-service components. Example, testing weld integrity by bending until failure. Non-destructive testing, NDT, methods, ultrasonic testing, UT detects internal flaws using high-frequency sound waves. Radiography, X-ray/CT visualizes internal structures via radiation. Magnetic particle inspection, MPI, asterisk, identifies surface cracks in ferromagnetic materials. Applications, quality control in aerospace, pipeline inspections, and historical artifact preservation. Advantages, preserves sample integrity, cost-effective for large-scale inspections. Case study, use of thermography in detecting delamination in aircraft composites. Comparison table, method DT/NDT key use pros cons tensile testing DT strength measurement high accuracy destroys sample ultrasonic testing NDT internal flaw detection no damage, portable requires skilled operator radiography NDT internal structure imaging detailed 3D images radiation hazards 8.2. Spectroscopy, microscopy, and X-ray diffraction spectroscopy, types, UV/IR, analyzes electronic/molecular transitions, e.g., polymer degradation. Energy dispersive X-ray spectroscopy, EDS, asterisk, identifies elemental composition in SEM, applications, quality control in pharmaceuticals, corrosion analysis. Microscopy, optical microscopy, surface morphology, up to 1,500x magnification. Electron microscopy, SEM, high-resolution surface imaging. TEM, atomic scale internal structure analysis. Example, SEM imaging of fracture surfaces to study crack origins. X-ray diffraction, XRD, principle, Bragg's law, n lambda equals 2d sin, to determine crystal structure. Applications, phase identification in metals, stress analysis in coatings. Case study, XRD analysis of archaeological ceramics to trace material origins. 8.3 Fatigue and fracture mechanics fatigue, mechanism, progressive crack growth under cyclic loading, e.g., rotating machinery. SN curve, plots stress amplitude versus cycles to failure. Testing, rotating beam tests, axial fatigue machines. Paris law, d/dn equals c, delta k, m models crack growth rate. Fracture mechanics, stress intensity factor, k predicts crack propagation, k equals y sigma, pi a. Fracture toughness, k_IC critical stress intensity for catastrophic failure. Applications, designing fail-safe structures, e.g., pressure vessels. Case studies, 1 Comet airline disasters, 1950s fatigue cracks from square windows led to explosive decompression. 2 Hyatt Regency walkway collapse, 1981 poor weld design exacerbated fatigue failure. Key takeaways, DT quantifies material limits, while NDT ensures operational safety. Spectroscopy/microscopy/XRD reveal composition and structure critical for performance. Fatigue/fracture mechanics prevent unexpected failures in cyclic load environments. Discussion questions, 1. Why might NDT be preferred for inspecting aging infrastructure? 2. How does XRD help in developing new alloys? 3. What design changes could mitigate fatigue in automotive components? Visual aids, SN curve for steel versus aluminum. SEM image of fatigue striations. Bragg's law diagram for XRD. This chapter equips readers to select appropriate testing methods and interpret results, ensuring material reliability in engineering applications. Chapter 9, Failure Analysis and Prevention 9.1 Root Cause Analysis of Material Failures Definition and Importance. Root cause analysis, RCA, is a systematic process to identify the fundamental causes of failures, ensuring corrective actions address underlying issues rather than symptoms. It is critical for improving material reliability, safety, and design practices. Methodology, 1. Problem definition, clearly articulate the failure, e.g., fracture, corrosion. 2. Data collection, gather evidence, failed components, operational records, environmental conditions. 3. Cause identification, use tools like the 5 whys or fishbone diagram to trace contributing factors. 4. Hypothesis testing, validate causes via simulations, material testing, or computational models. 5. Root cause determination, identify primary factors, e.g., material defect, design flaw. Common causes, material defects, inclusions, voids, or improper heat treatment. Design flaws, stress concentrations, inadequate safety factors. Operational misuse, overloading, exposure to unintended environments. Case examples: Challenger disaster, 1986 O-ring material failure at low temperatures. Hyatt Regency walkway collapse, 1981 design modification led to doubled stress on bolts. 9.2 Corrosion, wear, and degradation. Corrosion, electrochemical mechanisms, rust, iron oxidation, galvanic corrosion, dissimilar metals in contact. Prevention, coatings, paint, galvanization, cathodic protection, corrosion-resistant alloys, stainless steel. Wear, abrasive wear, hard particles erode surfaces, e.g., mining equipment. Adhesive wear, material transfer during sliding contact, e.g., engine pistons. Fatigue wear, cyclic loading causing surface cracks, e.g., bearings. Mitigation, lubrication, surface hardening, nitriding, material selection, ceramics for high wear resistance. Degradation, thermal, polymer embrittlement at high temperatures. UV/environmental, chain scission in plastics exposed to sunlight. Chemical, acid attack on concrete. Case example: pipeline corrosion, leaks due to soil acidity, prevented via epoxy coatings and sacrificial anodes. 9.3 Case study, the Tacoma Narrows Bridge collapse, 1940, background, design, slender, lightweight suspension bridge with solid plate girders. Nickname, galloping girder due to pronounced oscillations in wind. Failure analysis, primary cause, aeroelastic flutter, wind-induced torsional vibrations amplified by the bridge's flexibility and aerodynamic profile. Contributing factors, material choice, narrow, shallow girders lack stiffness. Design oversight, ignored aerodynamic stability in favor of cost and aesthetics. Lessons learned, design standards, adoption of open trusses for wind flow and wind tunnel testing. Material design synergy, importance of balancing material properties, stiffness, weight, with environmental loads. Legacy, modern bridges, e.g., Golden Gate Bridge, use stiffening trusses and aerodynamic shaping to prevent flutter. Key takeaways: RCA prevents recurrence by addressing root causes, not symptoms. Corrosion/wear/degradation are preventable through material selection, protective measures, and design. Interdisciplinary learning, failures like Tacoma Narrows highlight the need to integrate materials science, aerodynamics, and structural engineering. Discussion questions: 1. How might RCA differ for a material failure versus a design-induced failure? 2. Can advanced coatings eliminate corrosion in marine environments entirely? 3. What modern tools could have predicted the Tacoma Narrows collapse? Visual aids, fishbone diagram linking material, design, and environmental factors. Corrosion mechanisms illustrated via electrochemical cell diagrams. Comparison of Tacoma Narrows original design versus modern aerodynamic bridges. This chapter underscores the importance of holistic failure analysis, blending material science with engineering design to enhance resilience and safety. Chapter 10, Advanced and Emerging Materials. 10.1 Nanomaterials and Biomimetic Materials. Nanomaterials, definition: materials with structural features less than or equal to 100 nm, exhibiting unique properties due to quantum effects and high surface area to volume ratios. Examples: carbon nanotubes, CNT's exceptional strength, 63 GPa tensile, and conductivity for aerospace, electronics. Graphene, single-layer carbon lattice with high thermal/electrical conductivity, used in flexible screens and batteries. Quantum dots, Semiconductor nanoparticles for medical imaging and solar cells. Applications: lightweight composites, targeted drug delivery, energy storage. Biomimetic materials, definition, inspired by biological systems to solve engineering challenges. Lotus effect, superhydrophobic surfaces mimicking lotus leaves, self-cleaning coatings. Gecko-inspired adhesives, van der Waals force-based gripping for robotics. Spider silk composites, high toughness for impact-resistant armor. Case study, Shinkansen bullet train nose design inspired by kingfisher beaks to reduce noise. Comparison table, material inspiration application Velcro burdock plant fasteners morpho butterfly wings structural coloration anti-counterfeiting coatings 10.2 self-healing and shape memory alloys self-healing materials, mechanisms, microcapsules, release healing agents, e.g., polymers, epoxy, upon crack formation. Vascular networks, hollow channels replenish healing agents, inspired by human blood vessels. Applications: self-healing concrete, bacteria, Bacillus pseudofermis, precipitate calcite to seal cracks. Polymers, automotive coatings that repair scratches. Shape memory alloys, SMAs, mechanism, recover original shape via phase transformation, martensite left and right arrow austenite, when heated. Examples: nitinol asterisk, NITI used in medical stents, orthodontic wires, and robotic actuators. Copper-based SMAs, fire safety valves in HVAC systems. Case study, Mars rover wheels SMAs adapt to terrain, reducing wear. Innovations, 4D printing, SMAs in 3D printed structures that morph over time, e.g., adaptive building facades. 10.3 Sustainability in material development strategies, circular economy, recyclability, e.g., aluminum's infinite recyclability. Biodegradables, PLA plastics, mycelium-based packaging. Low-carbon materials, green steel, hydrogen-reduced iron ore, Hybrid initiative, 90% lower CO. Hempcrete, carbon-negative insulation alternative to concrete. Metrics, embodied carbon, total CO emissions from material extraction to disposal. Life cycle assessment, LCA evaluates environmental impact, e.g., cross-laminated timber versus steel. Case studies, 1EC3 tool, embodied carbon in construction. Microsoft's tool to track carbon in building materials. 2 Adidas X Parley shoes, ocean plastic upcycled into footwear. Challenges, scalability of bio-based materials. Balancing performance with eco-friendliness. Key takeaways, nanomaterials revolutionize industries with unmatched properties, while biomimetics bridges biology and engineering. Self-healing SMAs enhance durability and adaptability, reducing maintenance and waste. Sustainability drives innovation, prioritizing low-carbon, recyclable, and bio-inspired solutions. Discussion questions: 1. How might nanomaterials address energy storage challenges in renewable systems? 2. Can self-healing materials fully eliminate maintenance in infrastructure? 3. Should governments mandate LCA for all construction projects? Visual aids, infographic, life cycle of hempcrete versus traditional concrete. Diagram, microcapsule-based self-healing mechanism. Timeline, evolution of SMAs from lab to commercial use. Innovation spotlight, transparent wood, nanocellulose composite windows with better insulation than glass. This chapter illustrates how advanced materials are reshaping technology and sustainability, urging engineers to innovate responsibly for a resilient future. Chapter 11, Computational Materials Science 11.1 Molecular Dynamics Simulations Fundamentals, Principle, simulates atomic/molecular interactions over time using Newton's laws of motion. Force fields, mathematical models, e.g., Lennard-Jones, ReXFF, define interatomic forces. Integration algorithms, Verlet and velocity Verlet methods solve equations of motion. Applications, metals, study dislocation dynamics, crack propagation. Polymers, analyze chain entanglement, thermal behavior. Nanomaterials, predict graphene strength, carbon nanotube buckling. Limitations, timescale, nanoseconds to microseconds, and system size, millions of atoms. Constraints. Accuracy depends on force field parameterization. Case study, graphene's mechanical properties. MD simulations validated its theoretical strength, 130 GPa, before experimental confirmation. Software tools, LAMPS, Gromix, Material Studio. 11.2 Machine Learning for Material Discovery. Data-driven approaches, databases, Materials Project, OQMD, Open Quantum Materials Database. Feature engineering, descriptors, e.g., electronegativity, crystal symmetry, for predictive models. Algorithms, graph neural networks, GNNs predict properties from crystal structures. Generative models, design novel materials, e.g., inverse design of perovskites. Convolutional neural networks, CNNs analyze microscopy/spectroscopy images. Applications, accelerated discovery, high-entropy alloys with tailored hardness. Organic photovoltaics for solar cells. Property prediction, band gap, thermal conductivity, corrosion resistance. Challenges, data scarcity, experimental data versus synthetic data sets. Interpretability, black box models. Case studies, 1 Citron Informatics, ML platform optimizing battery materials for Tesla. 2 AlphaFold, protein structure prediction inspiring material informatics. Tools, TensorFlow, PyTorch, MatMiner. Key takeaways, MD simulations bridge atomic scale behavior to macroscopic properties. Machine learning revolutionizes material discovery, reducing trial and error R&D, synergy of computation and experimentation drives next-gen materials, e.g., fusion reactor alloys, biodegradable plastics. Discussion questions, 1 Can MD simulations ever fully replace physical testing? Why or why not? 2 How might biased training data impact ML predictions in material science? 3 What ethical issues arise from AI-driven material patents? Visual aids, schematic, MD workflow, initialization equilibration production analysis. Flowchart, ML pipeline for material discovery, data model validation synthesis. Heat map, ML predicted versus experimental material properties. Innovation spotlight, autonomous labs, self-driving labs, e.g., a lab at Berkeley, combine robotics, AI, and simulations for fully automated material synthesis. This chapter underscores how computational tools are democratizing material innovation, enabling faster, cheaper, and greener solutions to global challenges like energy storage and carbon capture. Chapter 12, Principles of Project Management. 12.1 Project Life Cycle and Methodologies, Agile, Waterfall, Project Life Cycle Phases. 1 Initiation, define scope, objectives, and stakeholders. Tools, project charter, feasibility studies. 2 Planning, develop schedules, budgets, and resource plans. Tools, work breakdown structure, WBS, Gantt charts. 3 Execution, implement plans, manage teams, and procure resources. 4 Monitoring and control, track progress, manage risks, and ensure quality. Tools, earned value management, EVM, KPIs. 5 Closure, deliver final product, conduct retrospectives, and document lessons learned. Methodologies, waterfall, linear approach, sequential phases, requirements design development testing deployment. Best 4, projects with fixed scope, e.g., bridge construction, manufacturing. Pros, clear milestones, predictable timelines. Cons, inflexible to changes, late testing. Case study, Hoover Dam strict phased execution due to fixed engineering requirements. Agile, iterative approach, sprints, 2-4 weeks, with continuous feedback. Frameworks, Scrum, Kanban. Best for dynamic projects, e.g., software, R&D. Pros, adaptability, stakeholder collaboration. Cons, less predictability, scope creep risks. Case study, Tesla's autopilot software frequent updates based on user feedback. Comparison table, aspect waterfall agile flexibility low high stakeholder input limited to early phases continuous risk management late stage issue detection early and iterative documentation extensive lightweight 12.2 stakeholder engagement and communication stakeholder identification, internal, project team, executives, contractors. External, clients, regulators, community groups, suppliers. Engagement strategies, 1 stakeholder analysis, map interest versus influence, power/interest grid. 2 RACI matrix, clarify roles, responsible, accountable, consulted, informed. 3 feedback loops, regular surveys, focus groups. Communication plan, channels, meetings, daily stand-ups, steering committees, emails, dashboards. Frequency, tailored to stakeholder needs, e.g., weekly reports for clients, monthly updates for regulators. Tools, Slack, Microsoft Teams, Trello, BIM 360 for collaborative workflows. Case studies, 1 failure, Boeing 737 MAX poor communication between engineers and regulators led to safety oversights. 2 success, Crossrail project, London, transparent stakeholder updates minimized community disruption. Conflict resolution, mediation, negotiation, and aligning incentives, e.g., shared milestones. Key takeaways, waterfall suits rigid, large-scale projects, Agile thrives in uncertainty. Stakeholder engagement requires tailored communication to balance competing priorities. Tools like RACI and power/interest grids prevent misalignment and scope drift. Discussion questions, 1. How would you adapt Agile for a construction project with fixed deadlines? 2. What risks arise when stakeholders are excluded from the planning phase? 3. Should regulatory bodies be classified as high-influence stakeholders in public infrastructure projects? Visual aids, Gantt chart, waterfall, versus Scrum board, Agile. Power/interest grid with stakeholder mapping. Communication flowchart for a hybrid Agile waterfall approach. This chapter equips readers to align project execution with organizational goals, fostering collaboration across disciplines while navigating constraints unique to structural engineering and materials-driven projects. Chapter 13, Planning and Scheduling 13.1 Work Breakdown Structures, WBS, Definition and Purpose. A work breakdown structure, WBS, hierarchically decomposes a project into smaller, manageable components, tasks, deliverables, or phases. It defines the total scope, ensuring no critical element is overlooked. Key components, Level 1, project title, e.g., high-rise tower construction. Level 2, major deliverables, e.g., design, material procurement, foundation, structural framing. Level 3, sub-deliverables, e.g., design conceptual design, structural calculations, permitting. Level 4, work packages, e.g., structural calculations beam analysis, column load tests. Creation process, 1. Identify major deliverables, align with project objectives. 2. Decompose into tasks, break down until tasks are actionable, 1-2 weeks duration. 3. Assign codes, use numbering, e.g., 1.1, 1.2, for tracking. 4. Validate with stakeholders, ensure completeness and clarity. Formats, tree structure, visual hierarchy. Outline, Text-based indentation. Tabular, spreadsheet with task IDs and descriptions. Example, WBS for a residential building, 1.1 Design 1.1.1 Architectural Plans, 1.1.2 Structural Engineering, 1.2 Construction 1.2.1 Foundation, 1.2.2 Framing. Case study, Sydney Opera House, initial WBS lacked detail on roof complexity, causing delays. Later revisions improved task clarity. Pitfalls, scope creep, adding tasks without adjusting timelines/budgets. Over-decomposition, excessive granularity complicates management. 13.2 Critical Path Method, CPM, and Gantt Charts. Critical Path Method, CPM, definition, identifies the longest sequence of dependent tasks, critical path, dictating project duration. Steps, 1. List tasks with durations and dependencies. 2. Calculate earliest start/finish, ES/F, and latest start/finish, LS/LF. 3. Determine float, LSES or LFF. 4. Critical path, tasks with zero float. Example, bridge construction, tasks, site survey, 5 days, foundation, 20 days, piers, 30 days, decking, 25 days. Critical path, 5 plus 20 plus 30 plus 25 equals 80 days. Gantt charts, visual tool, bars represent task timelines, showing start/end dates, dependencies, and progress. Software, Microsoft Project, Primavera P6, Smartsheet. Integration with CPM, Gantt charts visualize the critical path, often highlighted in red. Example, delays in piers extend the project end date. Case study, Hoover Dam, CPM streamlined coordination of concrete pouring and cooling, avoiding thermal cracking. Challenges, dynamic adjustments, revising schedules for unforeseen delays, e.g., weather. Resource conflicts, overlapping critical tasks requiring the same equipment. 13.3 Resource allocation and budgeting. Resource allocation, types, labor, equipment, materials. Techniques, resource leveling, adjust schedules to avoid overallocation. Resource smoothing, maintain resource limits without altering the critical path. Budgeting, 1. Cost estimation, direct costs, labor, $/hour, materials, $/unit. Indirect costs, overhead, permits. 2. Contingency reserves, 10-20% for risks, e.g., material price hikes. 3. Tracking, earned value management, EVM, compares planned value, PV, earned value, EV, and actual cost, AC. Example, high-rise project, crane rental, $10K/month, allocated to structural framing. Concrete delays. Contingency funds used for expedited shipping. Case study, Boston Big Dig, initial budget of $2.8 billion ballooned to $14.8 billion due to poor risk allocation and scope changes. Tools, ERP systems, SAP, Oracle for real-time budget tracking. BIM integration, Autodesk Revit links 3D models to cost databases. Key takeaways, WBS ensures comprehensive scope definition. CPM and Gantt charts optimize timelines and visualize progress. Resource/budget planning mitigates risks and aligns with project goals. Discussion questions, 1. How might a WBS differ for a bridge versus a software development project? 2. Can agile methodologies coexist with CPM in fast-paced engineering projects? 3. What strategies prevent budget overruns in material-intensive projects? Visual aids, WBS tree diagram for a skyscraper. Gantt chart with critical path highlighted. Resource histogram showing labor allocation. Innovation spotlight, AI-driven tools, Synchro Pro integrates 4D BIM with CPM for real-time scheduling. This chapter equips readers to master planning and scheduling, ensuring projects in structural design and materials analysis are delivered on time, within scope, and under budget. Chapter 14, Risk Management 14.1 Risk Identification and Mitigation Strategies. Risk identification, methods, brainstorming, engage multidisciplinary teams to list potential risks, e.g., design flaws, material shortages. SWOT analysis, evaluate strengths, weaknesses, opportunities, threats. Checklists, industry-specific templates, e.g., ASCE risk checklists for structural projects. Expert interviews, consult engineers, contractors, and insurers. Tools, risk matrix, plot likelihood versus impact to prioritize risks, see table below. FMEA, failure modes and effects analysis, quantify risks via severity, occurrence, and detectability scores. Common risks in structural projects, risk category examples design/technical calculation errors, software bugs, code changes. Material/supply quality defects, delays, price volatility. Environmental extreme weather, seismic activity, soil instability. Operational labor strikes, equipment failure, safety incidents. Mitigation strategies, design risks, peer reviews, BIM clash detection, redundancy in critical components. Material risks, dual sourcing, supplier audits, material testing, ASTM standards. Environmental risks, geotechnical surveys, seismic retrofitting, weather monitoring. Operational risks, safety training, equipment maintenance schedules, contingency staffing. Case study, Tacoma Narrows Bridge collapse, 1940, failure to identify aerodynamic instability led to catastrophic flutter. Modern mitigation, wind tunnel testing and aerodynamic shaping. 14.2 Contingency planning and insurance. Contingency planning, steps, 1. Allocate reserves, 10-20% of budget for unknowns, calculated via Monte Carlo simulations. 2. Develop response plans, predefined actions for high-priority risks, e.g., alternative suppliers for material shortages. 3. Scenario testing, simulate disruptions, e.g., delayed permits, to refine plans. Tools, risk register, tracks risks, triggers, and response actions. Schedule buffering, critical chain project management, CCPM, adds buffers to non-critical paths. Insurance mechanisms, type coverage. Example use case professional liability. Design errors, omissions. Engineers miscalculation in beam loads. Builders risk construction phase damage, fire, theft. Hurricane damage to unfinished structure. Performance bonds. Contractor default or delays. Contractor bankruptcy mid-project. Surety bonds. Compliance with permits and regulations. Regulatory fines for code violations. Case study, Boston Big Dig contingency budgets ballooned from $2.8 billion to $14.8 billion due to poor risk allocation and scope creep. Lessons, rigorous change order controls and transparent stakeholder communication. Key takeaways, risk identification requires systematic methods, e.g., FMEA, to avoid oversight. Mitigation reduces likelihood/impact, contingency plans prepare for residual risks. Insurance transfers financial risk, but proactive planning minimizes reliance on payouts. Discussion questions. 1. How might climate change reshape risk matrices for coastal infrastructure projects? 2. Can over-reliance on insurance discourage proactive risk mitigation? Explain. 3. Should contingency reserves be disclosed to clients? Why or why not? Visual aids, risk matrix, 5x5 grid, likelihood, rare to almost certain versus impact, negligible to catastrophic. Flowchart, contingency planning process from risk trigger to resolution. Infographic, insurance types mapped to project phases, design, construction, operation. This chapter equips teams to anticipate disruptions, align resources, and safeguard projects against financial and operational pitfalls, ensuring resilience in structural engineering and construction endeavors. Chapter 15, Team and Supply Chain Management 15.1 Leadership in Multidisciplinary Teams Overview. Multidisciplinary teams in structural projects integrate expertise from engineers, architects, contractors, environmental specialists, and project managers. Effective leadership ensures alignment, innovation, and timely delivery. Key principles: leadership styles, transformational leadership, inspire teams toward a shared vision, e.g., sustainable design goals. Situational leadership, adapt style to team maturity and project phase, e.g., directive during crises versus delegative in stable phases. Communication strategies, cross-functional meetings, regular sync UPS using BIM, building information modeling, for real-time collaboration. Digital tools, Slack, Microsoft Teams, or Aconex for centralized communication. Conflict resolution, mediation techniques to resolve clashes between architects, aesthetics, and engineers. Safety. RACI matrix to clarify roles: responsible, accountable, consulted, informed. Case study: Shanghai Tower, challenge, coordinating international architects, Gensler, with local engineers on wind load and seismic design. Solution: integrated BIM platforms enabled real-time updates, while agile sprints address design conflicts. Key takeaways: foster psychological safety to encourage innovation. Align team goals with project milestones using tools like Gantt charts. Discussion questions: 1. How can leaders balance creative freedom with technical constraints in multidisciplinary teams? 2. What digital tools are most effective for remote engineering teams? Visual aid, organizational chart mapping roles in a skyscraper project. 15.2 Procurement strategies and vendor relations. Procurement strategies, approaches: just-in-time, JIT minimize inventory costs, e.g., precast concrete delivery timed with construction phases. Sustainable sourcing, prioritize low-carbon materials, e.g., recycled steel, hempcrete. Global versus local, balance cost, global suppliers, with resilience, local vendors. Risk mitigation, dual sourcing for critical materials, e.g., seismic dampers, contracts with penalty clauses for delays. Vendor relations, evaluation criteria, quality, ISO certifications, sustainability, EC3 tool for carbon tracking, and financial stability. Technology integration, ERP systems, e.g., SAP, for real-time inventory tracking. Blockchain for transparent supply chains, e.g., conflict-free mineral sourcing. Case study: The Big Dig, Boston, challenge, cement shortages delayed tunnel construction. Solution: diversified suppliers and adopted JIT delivery, reducing downtime. Key takeaways: build long-term partnerships with vendors to ensure priority access during shortages. Use the KRLJIC matrix to categorize suppliers: strategic, leverage, bottleneck, non-critical. Discussion questions: 1. How can procurement strategies adapt to geopolitical disruptions, e.g., trade wars? 2. Should sustainability metrics outweigh cost in vendor selection? Visual aid, flowchart of procurement process from RFQ, request for quotation, to delivery. Innovation spotlight, AI in procurement, tools like IBM Watson predict material price trends and supplier risks. Circular economy, platforms like Reply enable material reuse across projects. Sustainability focus, embodied carbon tracking, tools like Tally, Revit plugin, assess material environmental impact. Ethical sourcing, audits for fair labor practices in steel and concrete production. Template, vendor evaluation checklist, includes criteria like lead time, carbon footprint, and disaster recovery plans. This chapter equips professionals to lead diverse teams and navigate supply chain complexities, ensuring projects meet technical, ethical, and sustainability benchmarks. Chapter 16, Quality Control and Assurance 16.1 ISO Standards and Six Sigma ISO Standards, Overview, ISO 9001, Quality Management Systems, QMS, ensuring consistency, customer satisfaction, and regulatory compliance. ISO 14001, Environmental Management Systems, EMS, for sustainable practices. ISO 45001, Occupational Health and Safety, critical for construction sites. Application in structural projects, documentation, standardized procedures for design, material testing, and inspections. Certification process, third-party audits to verify compliance. Case study, Skanska's ISO 14001 certification reduced waste by 30% in the UK's Crossrail project through eco-efficient practices. Six Sigma, methodology, DMAIC, define, measure, analyze, improve, control, to reduce defects. Define, scope issues, e.g., material defects in beams. Measure, collect data, e.g., defect rates via ASTM testing. Analyze, root cause analysis, e.g., faulty welding processes. Improve, implement solutions, e.g., automated welding systems. Control, sustain gains via statistical process control, SPC. Tools, process mapping, visualize workflows to identify bottlenecks. Fishbone diagrams, tackle causes of concrete cracking. Case study, Bechtel Six Sigma in LNG plants cut rework by 25% through data-driven weld inspections. Comparison, Aspect ISO Standard Six Sigma -- Focus Compliance and Consistency Defect Reduction and Process Excellence Framework Prescriptive Guidelines Data-Driven Problem Solving Certification External Audits Belt Levels, green/black, -16.2 Auditing and Continuous Improvement Auditing, Types, Internal, Self-Assessments to Preempt. Compliance Gaps. External, third-party audits for certifications, e.g., ISO. Process, 1 Planning, define scope, e.g., concrete batch plant operations. 2 Execution, review records, interview staff, inspect sites. 3 Reporting, highlight nonconformities, e.g., missing ASTM test logs. 4 Corrective actions, address gaps, e.g., retrain lab technicians. Case study, Fukushima Daiichi nuclear plant post-disaster audits revealed inadequate tsunami safeguards, prompting global nuclear safety reforms. Continuous improvement, methodologies, Kaizen, incremental improvements, e.g., reducing rebar cutting waste. PDCA cycle, plan, identify improvement, e.g., faster permit approvals. Do *, pilot digital permit tracking. Check *, measure time savings. Act *, scale successful solutions. Technology's role, BIM analytics, track design errors in real time. AI predictive maintenance, flag equipment failures before delays occur. Case study, Toyota's lean construction reduced bridge project timelines by 15% through just-in-time material delivery. Challenges and solutions, resistance to change, overcome via training and incentivizing innovation. Data overload, use dashboards, e.g., Power BI, to prioritize actionable insights. Key takeaways, ISO standards ensure baseline quality and safety, while Six Sigma drives precision and efficiency. Auditing validates compliance, and continuous improvement fosters innovation and adaptability. Integrating these systems reduces risks, costs, and environmental impact in structural projects. Discussion questions. 1. How might ISO 45001 prevent accidents in high-risk projects like tunnel boring? 2. Can Lean Six Sigma replace traditional quality control in construction? Why or why not? 3. What ethical dilemmas arise when balancing audit transparency with corporate confidentiality? Visual aids, flowchart, PDCA cycle in a retrofitting project. Heat map, common nonconformities in ISO 9001 audits. Timeline, Kaizen improvements in a skyscraper's elevator installation. Innovation spotlight, digital twins, simulate audits in virtual models to preempt real-world issues. This chapter underscores the synergy of compliance, data, and adaptability in achieving excellence, ensuring projects meet today's standards while evolving for tomorrow's challenges. Chapter 17, Digital Tools in Project Management 17.1 Software, Primavera, MS Project, Trello, Primavera P6, Overview, Industry Standard for Large-Scale, Complex Projects, e.g., Infrastructure, Oil and Gas. Key Features, Critical Path Method, CPM, with Resource Leveling. Earned Value Management, EVM, for Budget versus Progress Tracking. Multi-Project Management, Portfolio Level Oversight. Strengths, Robust Reporting, Integration with BIM and ERP systems. Weaknesses, Steep Learning Curve, High Licensing Costs. Case Study, Crossrail Project, London, coordinated 10,000 plus activities across 40 stations using Primavera. Microsoft Project, Overview, mid-tier tool for construction, IT, and manufacturing. Key features, Gantt charts with drag and drop scheduling. Resource management, allocate labor, equipment, and budgets. Cloud integration, sync with Teams and SharePoint. Strengths, user-friendly, scalable for small to medium projects. Weaknesses, limited advanced analytics. Case study, hospital renovation tracked phased construction to minimize patient disruption. Trello, overview, Agile/Kanban-based tool for task management. Key features, boards, lists, cards, visual workflow customization. Power UPS, integrate with Slack, Google Drive, and Jira. Strengths, flexibility, ideal for startups and remote teams. Weaknesses, lacks advanced scheduling, CPM, EVM. Case study, startup office build-out streamlined vendor coordination via shared boards. Comparison table, tool best for key strengths limitations Primavera P6 mega projects, $100M plus, advanced analytics, multi-project costly, complex interface MS project mid-sized projects integration with Office 365 limited EVM Trello Agile teams, small projects user-friendly, collaborative no CPM or resource leveling 17.2 BIM 4. Collaborative workflows BIM, building information modeling, definition, 3D model-centric approach integrating design, construction, and operations data. Key features, clash detection, identify conflicts between structural, MEP, and architectural systems. 4D scheduling, link model elements to timelines, e.g., Synchro, Navisworks. 5D cost integration, attach cost data to components, e.g., Revit and CostX. Collaboration tools, common data environment, CDE platforms like Autodesk BIM 360 or Trimble Connect for centralized access. Real-time updates, cloud-based model sync changes across disciplines. Benefits, reduced rework, clash detection cuts errors by 20-30%. Sustainability, energy analysis, e.g., Insight 360, optimizes HVAC and lighting. Life cycle management, facility managers use BIM for maintenance post-construction. Case study, Shanghai Tower BIM streamlined coordination of its twisted design, saving 30% in rework costs. Challenges, interoperability, software compatibility, e.g., Revit versus ArchiCAD. Training, upskilling teams in BIM workflows. Future trends, generative design, AI-driven tools, e.g., Autodesk Dynamo, automate design iterations. Digital twins, live BIM models for real-time asset monitoring. Key takeaways: Primavera/MS project/Trello cater to different project scales and methodologies. BIM transforms collaboration by unifying data across disciplines, reducing errors, and enhancing life cycle value. Integration of tools, e.g., BIM and Primavera, maximizes efficiency but requires interoperability planning. Discussion questions: 1. How might BIM evolve to address gaps in contractor-subcontractor collaboration? 2. Can Trello replace traditional PM software for small structural engineering firms? 3. What ethical concerns arise from AI-driven generative design in BIM? Visual aids, screenshot comparison, Primavera Gantt versus Trello board. BIM workflow diagram, from design to facility management. Infographic, cost savings from clash detection in BIM. Innovation spotlight, VR/AR in BIM, Oculus headsets for immersive design reviews. Blockchain for BIM, secure, transparent change logs in public infrastructure projects. This chapter equips professionals to leverage digital tools for precision, collaboration, and adaptability, ensuring projects meet modern demands for speed, sustainability, and stakeholder alignment. Case study: the Channel Tunnel Project. Project Management Analysis 1. Project Overview: the Channel Tunnel, CHUNNEL, completed in 1994, is a 50.5 km undersea rail tunnel connecting the UK and France. A landmark in engineering and international collaboration, it was delivered via a public-private partnership, PPP, involving Eurotunnel and contractors from both nations. The project cost £9 billion, double initial estimates, and involved 3 tunnels, 2 rail tunnels and a service tunnel. 2 key stakeholders, governments, UK and France, provided political support and regulatory frameworks. Private sector, Eurotunnel, concessionaire, Transmanche Link, TML, consortium, contractors, and financiers. Public, commuters, environmental groups, and local communities. 3 project management challenges: technical complexity, geology, differing strata, chalk marl on UK side versus fractured rock in France, required customized tunnel boring machines, TBMs. Alignment, precision engineering ensured tunnels met mid-channel, lasers and gyroscopes were used for surveying. Safety, high-risk environment led to incidents, including fires and flooding. Coordination and communication, multinational teams faced language barriers, differing labor laws, and disjointed reporting. Pre-digital error tools, fax, phones, slowed decision-making. Financial and contractual risks, over-optimistic revenue projections led to post-completion financial struggles. Disputes between TML and Eurotunnel resulted in costly litigation. Debt-heavy financing required government-backed assurances. Political and regulatory hurdles, aligning UK/French regulations on safety, labor, and environmental standards. Political shifts risked altering support or funding. 4 risk management strategies, geological surveys, extensive pre-construction studies inform TBM design. Contingency planning, buffer budgets and timelines for delays, e.g., TBM breakdowns. Risk allocation, private sector bore construction risks, governments handled political/legal risks. 5 execution and monitoring, phased construction, simultaneous tunneling from both coasts, with the service tunnel acting as a pilot. Quality control, rigorous safety protocols and real-time monitoring of tunnel integrity. Stakeholder engagement, regular updates to governments and public to mitigate opposition. 6 outcomes and lessons learned, successes, technical innovation, e.g., TBMs, waterproof tunnel segments. Symbol of cross-border collaboration, enabling economic integration. Shortcomings, financial miscalculations led to Eurotunnel's 2007 debt restructuring. Post-completion fires highlighted operational safety gaps. Key lessons: 1. Realistic forecasting, avoid over-optimistic traffic/revenue models. 2. Robust contracts, clear dispute resolution mechanisms to prevent delays. 3. Stakeholder alignment, continuous engagement with governments, investors, and communities. 4. Adaptive planning, flexibility to address unforeseen technical challenges. 7. Conclusion. The Channel Tunnel exemplifies the complexities of megaprojects, blending engineering prowess with intricate project management. While it achieved its technical goals, its financial struggles underscore the need for balanced risk allocation and prudent financial planning. Future projects can learn from its dual legacy of innovation and cautionary tales in stakeholder and risk management. Discussion questions. 1. How might modern digital tools, e.g., BIM, real-time data analytics, improve such a project today? 2. What alternative financing models could mitigate post-completion revenue risks? 3. How can international projects balance sovereign regulations without compromising efficiency? This case study serves as a multifaceted example of project management in action, highlighting both triumphs and pitfalls in one of history's most ambitious infrastructure endeavors. Chapter 19, Interdisciplinary Case Studies. 19.1 Sustainable Skyscraper Design, Structure and Materials and Management. 19.2 Offshore Wind Farm Development. 19.1 Sustainable Skyscraper Design Project Overview. A sustainable skyscraper integrates advanced structural engineering, eco-friendly materials, and life cycle management to minimize environmental impact while maximizing energy efficiency. Example: The Edge in Amsterdam or One Central Park in Sydney. Key features include: structure, lightweight, earthquake-resistant designs using composite materials. Materials: recycled steel, cross-laminated timber, CLT, low-carbon concrete, and photovoltaic glass. Systems: rainwater harvesting, solar panels, and AI-driven energy management. Key stakeholders: architects/engineers, design innovation and structural integrity. Contractors/suppliers, sourcing sustainable materials, e.g., cradle-to-cradle certified products. Governments, compliance with green building codes, e.g., LEED, BREEAM. Investors/tenants, balancing upfront costs with long-term energy savings. Interdisciplinary challenges. 1. Structural versus sustainability trade-offs. High-strength materials, e.g., CLT, may have fire safety risks. Energy-efficient designs, e.g., double-skin facades, complicate HVAC systems. 2. Material sourcing, limited availability of low-carbon concrete or recycled steel. Cost premiums for sustainable materials. 3. Management complexity, coordinating architects, engineers, and contractors to align with sustainability goals. Ensuring life cycle sustainability, maintenance, retrofitting. Risk management strategies, modular construction, prefabricated components reduce waste and speed up timelines. Digital twins, BIM, building information modeling, for real-time energy and structural simulations. Circular economy principles, designing for disassembly and material reuse. Outcomes and lessons learned, successes: 30–50% energy savings in certified green skyscrapers, improved urban air quality. Shortcomings: higher initial costs, 10–20% premium, deter investors. Key lessons: 1. Prioritize passive design, natural lighting/ventilation, over tech-heavy solutions. 2. Engage stakeholders early to align on sustainability benchmarks. 3. Leverage subsidies/tax breaks for green certifications. Discussion questions. 1. How can AI optimize energy use in skyscrapers without compromising occupant comfort? 2. What policy incentives are needed to scale low-carbon materials in construction? 3. How might climate change, e.g., extreme winds, reshape skyscraper design standards? 19.2 Offshore Wind Farm Development Project Overview. Offshore wind farms harness wind energy in marine environments, requiring coordination between marine engineering, environmental science, and grid management. Example: Hornsea Project, UK, or Hewine, Scotland, floating turbines. Key components: turbines, fixed bottom or floating designs for deep water sites. Grid integration, subsea cables and onshore substations. Environmental mitigation, protecting marine ecosystems during construction. Key stakeholders: governments, licensing, subsidies, e.g., feed-in tariffs and marine spatial planning. Energy companies, financing, construction, and operations. Environmental NGOs, monitoring impacts on seabirds, fish, and marine mammals. Local communities, balancing energy needs with fishing/tourism interests. Interdisciplinary challenges. 1. Technical complexity, harsh marine conditions, storms, corrosion, requiring durable materials. Floating turbine technology for deep water sites. 2. Environmental risks, noise pollution affecting marine life during pile driving. Collision risks for migratory birds. 3. Financial/regulatory risks, high upfront capital costs, $35 million per MW. Delays due to permitting or community opposition. Risk management strategies, adaptive marine surveys, using drones/AUVs, autonomous underwater vehicles, to map seabeds and monitor ecosystems. Stage development, phasing construction to test turbine performance and mitigate ecological impacts. Community benefit agreements, revenue sharing with local communities to secure social license. Outcomes and lessons learned, successes: offshore wind now supplies 10% of UK electricity, floating turbines unlock deeper waters. Shortcomings: high maintenance costs, cable failures disrupt energy transmission. Key lessons: 1. Invest in R&D for corrosion-resistant materials and modular turbine designs. 2. Collaborate with fisheries to design wind farm exclusion zones that protect livelihoods. 3. Use predictive analytics for maintenance, e.g., identifying turbine faults before failure. Discussion questions. 1. How can floating wind farms reduce costs to compete with fossil fuels? 2. What role should indigenous communities play in offshore wind planning? 3. How might climate change, e.g., rising sea levels, impact offshore wind infrastructure? Conclusion: both case studies highlight the critical role of interdisciplinary collaboration in tackling modern engineering challenges. Sustainable skyscrapers and offshore wind farms demand seamless integration of technical innovation, environmental stewardship, and stakeholder engagement. Their success hinges on adaptive management, transparent communication, and balancing short-term costs with long-term societal benefits. Key cross-cutting themes: digital tools, BIM, AI, as enablers of efficiency. Policy frameworks that incentivize sustainability. Community-centric approaches to mitigate opposition. These projects exemplify how merging expertise across fields can drive transformative solutions for a sustainable future. Chapter 20, Future Trends 20.1 AI-Driven Design and Automation 20.2 Circular Economy in Construction 20.1 AI-Driven Design and Automation Overview. AI-driven design and automation are revolutionizing the construction industry by enhancing efficiency, creativity, and precision. These technologies enable rapid iteration of design solutions, optimize resource allocation, and automate labor-intensive tasks, paving the way for smarter, faster, and safer projects. Key technologies and applications: generative design. AI algorithms generate multiple design iterations based on user-defined constraints, e.g., materials, budget, sustainability goals, enabling optimized solutions for structural efficiency and energy performance. Example: Autodesk's generative design tools used in the Airbus A320 partition redesign, reducing weight by 45%. Construction robotics, robots for bricklaying, e.g., SAM100, 3D printing of concrete structures, and autonomous drones for site monitoring and surveying. AI in project management, predictive analytics for risk assessment, real-time scheduling adjustments, and resource optimization. Example: Alice Technologies uses AI to simulate construction timelines and mitigate delays. Benefits: efficiency, reduces design time by automating repetitive tasks. Cost savings, minimizes material waste and labor costs. Innovation, enables complex, data-driven designs, e.g., biomimicry-inspired structures. Safety, AI-powered sensors detect hazards in real time, e.g., proximity alert systems. Challenges, high implementation costs, initial investment in AI software, hardware, and training. Workforce adaptation, resistance to change and skill gaps in existing labor pools. Data security, risks associated with sensitive project data stored in cloud-based AI systems. Ethical concerns, bias in AI algorithms and potential job displacement. Case studies: The Edge, Amsterdam, uses AI to optimize energy consumption and workspace utilization. Boston Dynamics Spot robot, deployed for autonomous site inspections in hazardous environments. Discussion questions. 1. How can AI address labor shortages in the construction industry? 2. What ethical frameworks are needed to govern AI decision-making in design? 3. Can AI-driven design coexist with traditional architectural practices? 20.2 Circular Economy in Construction Overview. The circular economy model aims to eliminate waste by reusing, recycling, and repurposing materials throughout a building's life cycle. This shift from a linear take-make-dispose approach is critical for achieving net zero carbon goals and resource efficiency. Key practices and innovations: design for disassembly, DFD modular components, e.g., cross-laminated timber panels, that can be easily dismantled and reused, material passports, digital records tracking materials' origins, properties, and reuse potential. Example: Modester platform catalogs materials in buildings for future circular use. Recycling technologies, advanced concrete recycling and bio-based materials, e.g., mycelium insulation. Industrial symbiosis, networks where waste from one project becomes feedstock for another, e.g., excess steel reused in neighboring developments. Benefits: sustainability, reduces landfill waste and embodied carbon, e.g., recycled steel cuts CO emissions by 50–80%, cost savings, long-term savings through material recovery and reduced virgin resource dependency. Regulatory compliance, aligns with EU Green Deal and corporate ESG targets. Challenges: high initial costs, premiums for recycled or bio-based materials. Supply chain fragmentation, lack of standardized systems for material recovery and resale. Regulatory barriers, outdated building codes that favor linear practices. Case studies: Circle House, Denmark, a residential project designed for 90% material reuse. Loop Industries, partners with construction firms to recycle plastic waste into building materials. Discussion questions. 1. How can policymakers incentivize circular practices, e.g., tax breaks for material reuse? 2. What role do consumers play in driving demand for circular construction? 3. Can circular economy principles be scaled for megaprojects like skyscrapers? Conclusion: AI-driven design and the circular economy represent two pillars of a sustainable, tech-enabled future for construction. While AI enhances efficiency and innovation, circular practices ensure resource resilience and environmental stewardship. Together, they address critical challenges like climate change, labor shortages, and waste management. Success hinges on collaboration, cross-industry partnerships to standardize circular systems, and AI integration. Policy innovation, governments mandating life cycle assessments and AI ethics guidelines. Education, upskilling workers to harness these technologies and practices. Key cross-cutting themes: digital twins for simulating circular material flows. AI's role in optimizing circular supply chains. Balancing automation with human-centric design. These trends underscore the need for interdisciplinary thinking, merging technology, sustainability, and economics to build a resilient built environment. Appendices: A glossary of key terms. 1. Public-private partnership, PPP, a contractual arrangement between government and private entities to deliver public infrastructure projects, sharing risks and rewards. 2. Tunnel boring machine, TBM, a machine used to excavate tunnels with a circular cross-section through varied soil and rock strata. 3. Building information modeling, BIM, a digital process for creating and managing 3D models of buildings, integrating data for design, construction, and operations. 4. Circular economy, an economic model emphasizing resource reuse, recycling, and waste reduction across a product's life cycle. 5. Generative design, AI-driven design exploration that generates optimized solutions based on user-defined constraints, e.g., materials, costs. 6. Cross-laminated timber, CLT, engineered wood panels used in sustainable construction for high strength and low carbon footprint. 7. Life cycle assessment, LCA, analysis of a project's environmental impact from raw material extraction to disposal. 8. Feed-in tariff, policy mechanism to accelerate renewable energy adoption by guaranteeing payments for energy fed into the grid. 9. Digital twin, a virtual replica of a physical asset used for simulation, monitoring, and optimization. 10. Embodied carbon, total CO emissions associated with material production, transportation, and construction. B. Reference tables, material properties, material density, kg/m superscript 3, compressive strength, MPa, thermal conductivity, W/mk, low carbon concrete 2430 50 0.81.2 structural steel 7852 50 450 cross laminated timber 480 1220 0.13 photovoltaic glass 2500 101.0 unit conversions quantity metric unit imperial unit conversion factor length 1 meter m, 3.28084 feet, foot, 1 m equals 3.28084 feet, force 1 kilonewton, kn, 224.809 lbf, 1 knot equals 224.809 lbf, pressure 1 mpa, 145.038 psi, 1 mpa equals 145.038 psi, energy 1 kilowatt hour 3.412 million BTU, 1 kilowatt hour equals 3.412 times 10 superscript 3 BTU-C. Software tools and resources, project management, Primavera P6, Oracle schedule planning and resource management for large-scale projects. Microsoft Project, task scheduling and collaboration tools. Alice Technologies, AI-driven construction simulation and optimization. Design and engineering, Autodesk Revit, BIM software for architectural and structural design. ANSYS, Finite Element Analysis, FIA, for structural and fluid dynamics. ArchiCAD, BIM tool for architects and engineers. Sustainability and circular economy, one-click LCA, life cycle assessment software for buildings. Modestur, platform for material passports and circularity tracking. AI and automation, TensorFlow, open source machine learning framework for generative design. Autodesk Generative Design, AI-powered design optimization. -D. Further reading and industry standards books, Sustainable Construction, Green Building Design and Delivery by Charles J. Keybert. The Lean Construction Institute Guide to Managing Risk by Paul D. Giammalvo. Industry Standards, ISO 14000, Environmental Management Standards. Bach Guide, Project Management Institute Best Practices in Project Management. LEED/BREEAM, Green Building Certification Systems. Reports and Journals, IPCC Special Report on Renewable Energy Sources, 2011. Journal of Construction Engineering and Management, ASCE. Online resources, Coursera, Construction Project Management, Columbia University. Autodesk University, free courses on BIM and generative design. Note, these appendices provide a concise reference for students and professionals, aligning with case studies and trends discussed in the textbook. Focus on usability, accuracy, and relevance to support interdisciplinary learning and application.